So we've finished talking about tetrahedral carbon compounds now. We're going to move on to planar carbon compounds. We've already ticked off alkenes and alkynes from this. I did make a note on Microsoft Teams about this on one of the posts, that I don't think we actually went into the specifics of the carbon to carbon double and triple bonds being planar, but go back and find that comment and let me know if you need any further clarification on it. In this video, I'll see how I'm doing for time. I'm going to try to get through aldehydes and ketones in this video, but we'll see how we get on. And just to note, any compound that we're talking about that has planar carbons, that means that there's a double bond going from the carbon to something else. We've seen where there's a double and a triple bond, and now we're going to look at some other substances. So the first one is aldehydes. An aldehyde is a compound containing a carbonyl group. So this is a carbonyl group here with at least one hydrogen attached to it. So the ending for aldehydes is al. So we have alcohols ending in al, aldehydes end in al from the beginning of their name. The functional group, so the ending of the name, is written as CHO. Now this is important because you need to identify the difference between CHO and COH, which is an alcohol. So COH is alcohol, CHO is an aldehyde. And this carbonyl group, they're strongly polar. So this is a very polar group here. Now the R here, I've written a note up in the corner. The R is used to represent the rest of the carbon chain. So the aldehyde that we have here, this is just the carbon with the oxygen bonded to it. The R represents all of the other carbons with hydrogens attached to them. So naming aldehydes, two of the simplest aldehydes are methanal and ethanal. So they also have other names that they're known by, but the IUPAC name that you would be expected to give is methanal. So again, meth for one carbon, and because the bonding to that carbon would be single bonded, and al because we've got the CHO group here. This is ethanal, two carbons. The first carbon here is double bonded to the oxygen, that's our carbonyl group, and that carbon has to be bonded to at least one hydrogen, and there's our hydrogen. So aromatic aldehyde, so that's an aldehyde group on a ring structure or on a benzene ring, include oil of almonds, vanillin, and oil of cinnamon. So just looking at our aldehydes, you can see here they are similar to the alcohols, and that's why when we were talking about alcohols, I was saying it's very important to show the COH when you're drawing them out. And the same for aldehydes here, CHO, you have to write CHO. If you wrote COH, it would be read as an alcohol. So again, the naming is the same as we've always done, and because you have to have one hydrogen on the carbon, aldehydes, the aldehyde functional group is always going to be on the first carbon. So that's why we don't have any numbers here. So methanal is a carbon with two hydrogens attached to it and double bonded to an oxygen. Ethanal, here's our carbonyl group, one hydrogen attached to that carbon, and then we've got the rest of the carbon chain. Propanal, again, you'll see all of these, the aldehyde group has to be on the end. If we had a double bond to oxygen here, that would be a ketone that we're going to see in a second. The carbon wouldn't be able to have another bond to a hydrogen, which if we go back up here, which I think we should, the carbonyl group has to have at least one hydrogen attached to it, and that can only happen on the first carbon in the chain. Benzaldehyde is an aromatic aldehyde that we spoke briefly about earlier on, and it's found in almond kernels, and this is the structure of it here. Benzene ring with the aldehyde group attached to it. Physical properties, they're all liquids except methanal, which is a gas at room temperature. The boiling points are higher than corresponding alkanes due to the polar carbonyl group, but they're lower than corresponding alcohols. Now think about what the reason for that might be. Um, the reason it would be is because the alcohol group can form, the hydroxyl group, sorry, can form hydrogen bonding. Short chain aldehydes are soluble in water due to the polar carbonyl group. As the number of carbon atoms in the molecule increases, solubility in water decreases while solubility in cyclohexane increases. Exact same sentence that we would have used for the alcohol, but we've replaced alcohol with aldehyde here. Just looking at the boiling points for our alkanes, aldehydes and alcohols, you can see the comparison there. With the aldehydes, the dipole-dipole attraction as well as dispersion forces. It has a boiling point higher than the similarly sized alkane, which only has dispersion forces. However, the aldehyde's boiling point isn't as high as the alcohol because in the alcohol it can have hydrogen bonding. On to the next one. So we'll tick off aldehydes there. Ketones are next. Ketones are similar to aldehydes, very similar in fact. They have the carbonyl group, but instead of having a hydrogen attached here, we have another carbon chain. So this time it's, so for the aldehydes we had R, and one of these had to be a hydrogen. This time it's not. This is where we put the functional group, the carbonyl group, in the middle of the compound. Physical properties are similar to aldehydes due to the dipole-dipole forces. Their solubility is very similar to the aldehydes. And since propanone, acetone and butanone can act as solvents in both polar and non-polar solvents, they are widely used in industry. So if we just have a look at these here, the carbonyl group is in the middle of the compound rather than at the first carbon. Ketones never have a hydrogen atom attached to the carbonyl group. So aldehydes, you have your functional group is the carbonyl group, and that carbon will be attached to one hydrogen always. If there's two carbons attached here, that must mean it's a ketone. And the names for them, again, propan is the same as naming propane, but the ending changes to -one. And so the way they're written is that you would write CH3 for this group, then you would write CO, no need for brackets here because that's the only thing that that carbon can be bonded to because of the double bond, and then CH3. So this one, just to call it out for you, would be CH3, CO, CH2, CH3. You do need to number these. So for the aldehydes you don't, because it has to be on the first one. You do have to number ketones. For example, pentan 3-one, that could also be pentan 2-one if the carbonyl group was on one of these two. Just to show you the structure of what they look like. Again, very similar to the alkane in the way we draw it out, but instead of putting on two hydrogens here, you replace those with a double bond to oxygen. Physical properties. Butanone and propanone are liquids at room temperature. Their boiling points are higher than corresponding alkanes, but lower than corresponding alcohols, all for the same reasons as the aldehyde group. Higher than alkanes because of the polarity of the carbonyl group, lower than alcohols because of the hydrogen bonding possible with the hydroxyl group in the alcohols. Short chain ketones are soluble in water due to the polar carbonyl group. Ketones are soluble in non-polar solvents such as cyclohexane. So as the carbon chain gets longer again, there's more non-polar parts to it, or a longer chain of non-polarity, so that cancels out the polar carbonyl group. Uses of propanone. Propanone is used as a solvent. So we saw a while ago that I actually didn't mention very much about. Propanone, the more common name for it is acetone. And acetone, for anyone that has used nail varnish remover or has smelt it, that's the substance used in it. So here are your questions on aldehydes and ketones. Give those a go and submit them over on Microsoft Teams.